Science, technology, engineering, mathematics, the four core pillars of STEM education, have been deeply intertwined throughout the history of human civilization, forming an inseparable system of knowledge and practice. If we turn back the clock thousands of years, people were already building houses, digging wells, irrigating farmlands, and brewing wine. At that time, there were no modern scientific theories or mathematical models to guide them. Yet behind these ancient practices lay the hidden laws of physics, the principles of geometry, and the seeds of quantitative and computational thinking. In other words, long before systematic science existed, humans were already practicing science through intuition and experience, and applying mathematics in real life. So, from a historical perspective, engineering and technology originally emerged as direct responses to the real world, shaped through repeated trial and error, and gradually refined through accumulated experience. Science and mathematics, on the other hand, often came afterward, built through abstraction and induction, forming structured theoretical systems based on those practical experiences. As we moved into the modern era, especially when engineering reached its limits, science and mathematics became the key to further breakthroughs. With the maturation of mechanics, electromagnetism, materials science, and thermodynamics, engineering no longer relied solely on experience, but shifted toward theory-driven design. For example, aircraft design depends on aerodynamics, chip manufacturing relies on materials science and quantum mechanics, and large-scale bridge construction must be simulated and analyzed using structural mechanics and calculus. This shows that modern engineering depends more and more on strong support from science and mathematics. At the same time, science, math, engineering, and technology are becoming more deeply connected and mutually reinforcing. However, these four core elements, which should be integrated, are often separated in today's education system. Math and physics students derive formulas step by step and focus on theoretical beauty, but often don't know how those formulas apply to real engineering problems. Engineering and computer science students, on the other hand, focus on getting the code to run and gradually ignore mathematical rigor and underlying principles. This not only limits their understanding of advanced technologies, but also keeps engineering at the application level, making further optimization and progress difficult. In many universities, first and second year students spend countless hours proving theorems in calculus, manipulating endless matrices, and struggling through the dry symbols and definitions of digital and analog circuits. Even when they finally enter the lab, the experiments before them often feel disconnected from real life, making it hard to link what they learn to the world they live in. Professors often say, build a solid foundation and applications will come naturally in the future, but the problem is the path from theory to practice is too long, so long that many lose their passion, their sense of purpose, and even the curiosity that started it all. So let's think about this the other way around. What if, from the very first day, we learn scientific principles and mathematical formulas, we can already see their meaning and understand how they are used? What if the knowledge we learn every day is not for exams, but for solving real problems, for building hands-on interactive projects? So the question is, can learning be more motivating, more focused, and more meaningful? This is the idea I want to explore with you in my STEM study space. We will study calculus and discrete mathematics, while also learning the history, context, and meaning behind each formula and use visualization to make abstract ideas visible. After learning the relationship between current and voltage, we will immediately build and light up a simple circuit to test, deepen our understanding, and turn scientific knowledge into real applications. You don't need a big space and you don't need expensive equipment. Together, we'll explore how to use simple tools to build our own home science and engineering lab right in a corner of your home on a single desk. In this lab, we're trying something very special and very important, reconnecting knowledge that has been split apart. We no longer treat math, physics, circuits, and programming as isolated subjects. Instead, we bring them all back to a real tabletop and fuse them into projects you can see, move, and interact with. Here we will build together a robotic hand that simulates grasping, a code-controlled robotic arm, a DIY game console, and a set of traffic lights that simulate the real world. Behind every project are math models, sensor principles, structural design, and program logic. And in this process, you are no longer just a student. You are a builder, a debugger, and a creator. It's true that AI is rapidly replacing more and more repetitive, simple jobs. So, what kind of people will the future really need? The future doesn't just need people who are good at exams or coding, it needs interdisciplinary thinkers, those who can move freely between science, technology, engineering, and mathematics. People who understand core principles and can build with their hands. People who can work with AI and also ask AI new questions. This is what we are working toward in the STEM study space, reconnecting fragmented knowledge and turning abstract ideas into real world power. Together, we strive to become STEM creators with depth, creativity, and purpose, ready for today and for the future.